Good afternoon, everyone. I'm Chris Shaver, and I'm going to talk a little bit about heterogeneous modeling in Ptolemy. I'm part of Edward Lee's group. So different kinds of systems have different kinds of underlying intuitions about their semantics. And because those different systems have different underlying intuitions, different models of computation can be used to design these systems. When you use different models of computation, you have a different underlying semantics, you have a different way of transmitting information, determining how execution functions, and reasoning about how these models work. In models that are more complex, you might have several models of computation all describing different parts of a system. These parts then have to come together and interoperate with each other, even though their semantics are different for different parts. A continuous time model might be involved in some kind of a simulation, whereas data flow might be involved in some kind of signal processing, all in one system. Interoperability becomes an interesting question both programmatically and formally. Programmatically, you have to get all these semantics to function with each other in a predictable and coherent way. Formally, also, you need a means to reason about these semantics and figure out what does it mean to be deterministic or what does it mean to be monotonic when you have different models of computation interacting with each other. So tools need to be developed for this to work. The Ptolemy II project is a software package and an open source research platform that's used to investigate and understand heterogeneous modeling. It's an actor-oriented language, so it's based on actors as the fundamental element, and it's easily extensible and implements many models of computation. It's around 2.5 million lines of code, and it has many different features that are used in different industries or experimented with in different industries. The basis of this model, or the basis of this overall model, are the actors. The actors are individual elements, atomic elements that have inputs, outputs, state, and function within a larger context. This larger context start up being actor graphs. An actor graph is a bunch of actors connected together by their input ports and their output ports. And by these input and output port connections, they can communicate with each other and organize their execution. To actually do this semantic organization of execution and transmission of data, a director is added to an actor graph. This director imposes onto this actor graph an interpretation that is that model of computation. There are different models of computation that are very diverse and one can think of it in very different ways from one another. A big class of models of computation are data flow models of computation, where the actors communicate by passing tokens through perfect queues, and there are a ton of different variants of this model of computation, all with their own constraints, their own guarantees, and their own logic. Synchronous directors or synchronous models of computation are another class and very different. They have a series of iterations, each of which determine a single value on each one of the relations between inputs and outputs of actors. When you take a model built up from an actor graph and a director, giving it a semantics, you can contain that model in an actor in and of itself. And these actors are called composite actors. Using composite actors, you can create hierarchical models. And these hierarchical models then have diverse sets of models of computation at different levels. To reason about this formally, we've developed an idea called modular actor interfaces. Modular actor interfaces gives the actor a model that has inputs, outputs, and state, and 4 functions that determine its dynamic semantics: a fire function, post-fire, deadline, and time update. So the fire and post-fire function are very much like a Mealy machine. They take inputs and outputs, the fire function, and produces, or it takes inputs and states rather, and produces an output, and then updates the state by taking inputs and state and calling a post-fire function. To deal with models of computation that have to do with time, which are very important in Ptolemy, there's a deadline function, which determines when the actor has to next fire based on its inputs and its state. Finally, there's another kind of state transformation that performs a slightly different function in most models of computation, and it's the time update function. It also updates the state, but also takes into account time as part of its inputs. When you put these these formal models together, you get an actor graph, again, as you do with the programming practice. A director then becomes a way to take this actor graph with all of its constituting interfaces and formally combine them into a new actor. And so this can be done mathematically. And a mathematical representation can be given to what a director does, and therefore the model of computation, the semantics can be reasoned about in mathematical terms. This is an example of a formal way of describing the fire function of the synchronous reactive director in terms of a fixed point of a function. And so one can prove theorems about these. There's a model of computation called the coroutine model of computation that I've been working on. And in this model of computation, a result can be proved. There are two results here. One, which is particularly important, is the second theorem, which says that when you take actors that have a certain property, that have the property of monotonicity, and you combine them together with this model of computation, the entire model is also monotonic. So in conclusion, try out Ptolemy. It's free and it's open source, and it's worth checking out to understand how to interact with different models of computation. Look at modular actor interfaces. I'm going to have a poster on the coroutine model of computation in the DOP Center in Corey. Thank you.